Hi, so today I want to show you how to use the FastDHC tool. You can find the FastDHC tool here at ies-apps.art.ac.at, where you can find several other apps, among which is the FastDHC app. So let's go to the tool. Here on the first page, you can find an overview of the project, links to the project website, the LinkedIn page, and the partners. And then let's go to the tool. In general, the FastDHC tool has two input sections. We have the input section on the left and the results section on the right. The idea is that if you change something in inputs, you can immediately see it in the results section. The most important part of the results section is the results plot, which compares the three compared systems within the FastDHC tool. We have fourth generation district heating, thermal source network, or also commonly referred to as fifth generation district heating, and the individual system where every household has their own heat supply. This plot compares the total annualized costs by the system and also breaks down the cost structure, so you can see what's the greatest cost drivers here. For example, we have the air water heat pump and the electricity of the households for the individual system. On the left, in the input section, we have three parts. We have the general input, the demand input, and the supply input. In the general input, we can select the country. At the moment, this is Austria, United Kingdom, Denmark, three project countries. We can select the area type, which is city, rural, or suburban, which influences later the network length calculation. We have the heating degree days temperature, which is below which heating is required. This differs from country to country, so you can select a range from 12 to 15 degrees, which influences also the full load hours of heating and the full load hours of cooling. So you can see if we switch here, we have 1560, and we can also change this manually if you feel like this is not fitting to your system. Also, we have the average household size, influences some of the sizing aspects regarding domestic hot water, and we have the discounting factor to get the total annualized costs later on. So if we go to the demand section, we have 5 different parts here. We have the buildings in general, we have the heating of the buildings, cooling of the buildings, domestic hot water, and the overview to adapt the values once again. So if we start with the buildings, we have three types here. We have single family homes, apartment buildings, and non-residential buildings. First, we can put in the number of the buildings, and also we can put in how many dwellings or individual apartments we have per building. This is of course only relevant for apartment buildings. Also, we have, depending on the country, the average floor space per building as a default value, and we can still adapt this if we feel like this is not how it's in the individual country. And then we have the ratio of the buildings based on existing and new, so we can just put in, like, if we say it's all existing or if it's all new. Same goes for apartment buildings and non-residential buildings. This is based on the tabular database and grouped before 2000 as existing and after 2000 as new. So this is a simplified version. Furthermore, we have also the heating type. We can switch between floor heating, which is 30 degrees, and radiator heating, which is 55 degrees. But we can adapt this later on once again. And then for the new buildings, we have the same slider where we can adapt between radiator and floor buildings. And as you can see on the right, when we change something here, it slightly adapts based on the inputs we give here. So let's go to the heating part. Here we can adapt the heat loads in watts per square meters. These are again based on the tabular database and the average for existing and new buildings. The temperature for floor heating. The default values are 40 degrees for existing buildings and 30 degrees for new buildings. The same goes for radiator heating, where we have existing buildings at 60 degrees and new buildings at 50 degrees. For cooling, we can also adapt the cooling load in watts per square meters. Here we find the default values, and we can again adapt this in watts per square meter when we find this is not fitting. We can adapt the cooling supply temperature, which is at the moment 15 degrees. And we can also specify whether the cooling, so the waste heat from the cooling, should be reused within the building for domestic hot water. So we just put a tick here. And we can also then, for the non-residential buildings, specify whether the waste heat from cooling should be used in the network to then reuse it. But we have to apply a storage element later on. Going to domestic hot water, we have the kilowatts per square meter per year as default values for the 3 house types, and we can again adapt them here. The general temperature is set at 60 degrees, which is a standard value here, but for domestic hot water, for single family homes, this value might be lower as regulations are less strict. But again, this is up to the user. And then we can also select whether we use a storage for domestic hot water, which would bring down the estimated capacity we have to consider for domestic hot water in the buildings. So we can see here now, for example, we have 102 kilowatts per building estimated for the apartment buildings. And if we select a storage, it will automatically suggest a certain storage capacity, and it will bring down the capacity to 85 here. So, and then in the overview, we can still adapt all the values. We have the overview, like what's the estimations here for seasonal and annually. And here we can, for example, if this is too low, we just adapt it here, and the same goes for space heating and for domestic hot water. And we can also see the values we have that came out here in the demand plot. We can see for each of the building types and for cooling, domestic hot water, and heating, how the demand would look like. And if we adapt something here, let's say this is much higher, let's say it's 10,000, it will automatically adapt this and consider it in the calculation. Okay, so now let's go to the supply. And this starts here with the source. The idea is that we are based in terms of central source. Of course, only the thermal source network and the 4th generation district heating are relevant. And we can switch here between a heat pump or heat exchanger, depending on the source temperature, and a boiler. And the idea is that based on the estimated capacity that has to be provided, it's either 50-50 or in this case 100% for the heat pump or 100% for the boiler. And this will affect then the costs later on. If we say the boiler is smaller, then automatically an air heat pump is considered as a backup if this is not sufficient. But we can then change it back to the estimated capacity so that we can cover everything. And here we also see a summary of the decentral heat pumps, so that are installed in the buildings to, for example, supply domestic hot water at 60 degrees, depending on the network temperatures in the out. So here we can adapt the values for the backup. This is calculated internally, and also the decentral heat pumps are also calculated internally. Regarding the heat source for the network, we have a wide variety here. For example, if we choose food and drink, and we have some default source temperature here that we can adapt if we feel like it, or we say we just go with it. And we can also say if the source is limited, for example, we only have a certain megawatts available, we can put a yes here, and then we can specify how it is limited or if it is limited. For the central boiler, we can select different types of sources, which also affect the capex later on and the energy prices. Let's put electric here, for example. And then here we also see the efficiencies of the heat pumps, and for 4th generation and for 5th generation. And the same goes for the boiler. As it's electric, it's set here at 0.99, 99% efficiency. Okay, let's go to the distribution now. This is mainly an overview as we fixed the network temperatures here. So we have 65 as a supply temperature and 30 as a return temperature for the 4th generation. And for the thermal source network, we have 15 degrees as supply temperature and 5 degrees as a return temperature. And this also is related then to the pipe losses. We can set here annual pipe losses for 4th generation. This is set at 10%, and for the thermal source networks, this is set at 1%, taking into consideration the annual ground temperature for the distribution of the pipe losses. And then if we go on to network length, here we have, based on the number of buildings and the area we are in, an estimation of the pipe length. And of course, this is a very high level and generalized assumption. So these values might be very different depending on building density and all that. So the idea is that this is an estimation, and that you can still adapt this if this is not the way you see it. And for storage, we have two options here. We have seasonal storage to get the excess heat from cooling. So we will put a yes here. We can select the share, how much you want to store. And then depending on if we say we have excess cooling, it will calculate a volume, as it's a tank storage considered for the 4th generation, and an area for boreholes if it's for the 5th generation thermal source network. And in this case, it is like there's no excess heat to be stored, so it remains at 0. The other option is the diurnal storage for to lower electricity prices. The idea is that if the storage would sort of pay for itself, considering annualized costs, and which would lower than the heat pump, the electricity for the central heat pump. So in this case, the suggestion would be a 4,000 cubic meter storage. This is quite big, of course. And here we have no suggestion because the annualized capex does not outweigh the benefits of the electricity savings. And at the very last, we have the energy prices. We have costs for the heat source for the heat pump. This could be development source. This could be some sort of payment for a waste heat owner. So you could consider here the annuity of developing the source, or like I said, a payment for the waste heat provider. We have the fuel for the boiler, which you can specify here. And for the electricity prices, we can either use annual average prices, or we can say we use bands. That means we set for 0 to 1 megawatt hour, 1 to 2.5 megawatt hours, we can set certain prices. And this is for households and also for non-households. So here for the non-households, of course, this is much larger. We can say from 0 to 20 megawatt hours, we have 300, and then going up to 150,000 megawatt hours, 240 euro per megawatt hour. Again, these are default values depending on the country, and if we say this is too much or too little, we can again adapt the prices to see then what's the outcome. And overall, we have the graphic visualization of the costs here, and we also have a results summary. We have demands for space heating, hot water, and cooling for each of the solutions. We have the installed heat pump capacity, the total cooling capacity, the estimated network length, storage size, total capex in 1,000 euros, total opex in 1,000 euros per year, and the total annualized costs as a comparison, and also the levelized costs of energy. In the demand plots, we can see what demands were considered. In the detailed demand data, we can go dig deeper into the data and find out which assumptions were made. In electricity, we can find the distribution on the different building types. Seasonal demand data shows an aggregated values of that. System inputs data shows the central side of the systems. And then we have also final analyzed cost data, which are the basis for the plot we saw in the beginning. So we can have the numbers here. And also diurnal storage data is how much we can save using diurnal storage. Yeah, so overall, this was the FastDHC tool. And thank you for listening.